Okay. I think we're recording. I hope we're recording. We're supposed to talk about 5.3 before we do, or 3.4, 5.3 today. Before we do, hey, somebody needs to mute their mic, whoever has some family or something in the background.
I'm sorry.
Yes, that's okay. Tell your family I said hello. Okay. Section 5.3. Before we start this, I need to go back and just mention something that you saw in 5.2, and that was the definition of the area of a region in the plane. We're into the second branch of calculus now, where we're going to be undoing what we did the first part of the semester. First part of the semester, we were differentiating. Now we're going to be integrating, and we're talking about what the integral gives us. So before we talk specifically about the definite integral, you know what an antiderivative is? An antiderivative, or it's also called an indefinite integral, is just the function whose derivative is a given value. Not a given value, but a given function. If I tell you to find the derivative, for example, of 3x squared, can you tell me what function would have as its derivative 3x squared?
X cubed.
X cubed, right. And then we kind of left that for a while. We talked about antiderivatives in 5.1, and then we kind of left it and started talking about new symbols, such as the summation symbol, and how to evaluate sums using that summation symbol, different formulas that you can use. And this section is going to tie those two things back together, what antiderivative has to do with area. Let me make sure that you understand this definition of area. It's cool. And did I have this paper with the sideways writing on it in Momentum? I believe I did, as part of your notes.
Yep.
Okay, good. Because this really helps you understand what this definition is. If delta x is the width of a rectangle, and you get the width of a rectangle, well, let me start here. Let f be a continuous, let f be continuous and non-negative on the interval from a to b, and that's a closed interval because of those brackets. The area of the region bounded by the graph of the function, the x-axis, and the vertical lines x equals a and x equals b is given by this crazy looking formula. And looking at that picture, here is a function that is continuous and non-negative from here to here, bounded by the vertical lines x equals a and x equals b. That area can be found by, shoot, I forgot which Greek was it. Yes, it was Archimedes. Archimedes developed the method of exhaustion for finding the area of irregular shapes. And what he did was he took an irregular shape and divided it into a whole bunch of regular shapes we have formulas for. For example, if you divide that shape I just made into a bunch of triangles, then you can find the area of each one of those triangles and add them all up, and you'll have the area of that shape. And Archimedes was the one who said, let's just use more and more and more triangles. I just divided that shape up into 1, 2, 3, 4, 5, 6. Well, that's not really a triangle, but play like it is. My drawing's not perfect there. I divided that irregular polygon up into, what did I say, 6 different triangles. And if I had used 20 or 30 or 100 or 200 triangles, the more triangles I'd use, the better approximation I would get of the area of that irregular polygon. So this definition comes from that idea. If you let the number of, here we're going to use rectangles instead of triangles, but if we let the number of rectangles increase without bound, and we add up the area of each rectangle, the area of each rectangle would be the width of each rectangle times the height of each rectangle. The width of each rectangle comes by just dividing the length of the interval. The length of the interval is b minus a. If you divide the length of the interval by the number of rectangles, then you have the width of each rectangle. And that makes sense. The width of each rectangle is the length of the area divided by the number of rectangles. So if we let that number of rectangles increase without bound, and this summation symbol just says add up all of the areas of these rectangles where f of c sub I, the height of the ith rectangle, times the width of the ith rectangle, add up all those areas, and that will give you the area under this curve, bounded by the x-axis and the vertical lines x equals a and x equals b. So as weird as that notation looks, if you just had seen that on a side of a building a year ago, it would have made no sense at all. Now I want you to look at it and go, well, that's just adding up the area of a bunch of rectangles. And that's how we find area under a curve. All right, so the first thing on today's notes is just that definition again, because we had to talk about that weird looking definition. And notice that definition has the conditions that f be non-negative and all of our rectangles are the same width. All of our rectangles are the length of each of the interval divided by the number of rectangles. Well, going just a little bit beyond that, taking off those two restrictions and allowing us to talk about functions that are below the x-axis in some places and not using the same width for all rectangles, then we have what's called the Riemann sum. The Riemann sum, f of c sub I, is still the height of the ith rectangle, and delta x sub I is still the width of each rectangle, but all rectangles don't have to be the same width now. So a Riemann sum is just an extension of this definition to include where the function's negative and the fact that all rectangles don't have to be the same width. Now, hang with me a minute. The width of the largest subinterval of a partition delta, delta is just one of the rectangles. The width of the largest subinterval of a partition delta is called the norm of the partition, and it's denoted by, kind of looks like a double absolute value. When you see that symbol, that's just the width of the largest rectangle. And that width going to 0 means the same thing as the number of rectangles going to infinity. As the number of rectangles goes to infinity, the width of each rectangle is going to be going to 0. So the definition of the definite integral, and this deserves a drum roll, this is big. The definition of the definite integral is given as a limit of the Riemann sum as the partition of, I ran out of words there, as the width of the rectangles goes to 0 rather than as n goes to infinity. Now, you'll remember how weird the definition of the derivative looked the first time you saw it. The limit as h goes to 0 of f of x plus h minus f of x over h looked absolutely bizarre, but then you found out this is just the difference in two y's. This is the difference in two x's as the two x's get closer and closer. So you found out that that gave you an instantaneous slope, an instantaneous rate of change, or the derivative actually gives you a formula for finding the slope of a curve at any point. Likewise, when you see this definition of the definite integral, I want you to think that's just adding up the height and the width. Height times width gives me area, so I'm adding up the area of a bunch of rectangles as the number of rectangles goes to infinity, and that means the width of each rectangle is going to 0. That is the definition of the definite integral, just like this is the definition of the derivative. All right, that was a complicated little spiel. Does anybody have any questions before we go on? Anybody feel like I didn't understand that well enough to ask a question? Then I take that to mean everybody's going, okay, I can see that that's adding up a bunch of areas of rectangles. And that's exactly what the definite integral does. When we talked about antiderivatives in 5.1, we didn't have this A and B on the integral symbol. Those are called the bounds of immigration, or bounds of integration, or the limits of integration. A is called the lower limit of integration, B is the upper limit of integration, and A to B is the interval over which the function's being anti-differentiated. It's not a coincidence that the notation used for the definite integral is similar to that used for indefinite integrals. You'll really see why you can use the same notation for the definite integral as the integral, as the antiderivative when we talk about the fundamental theorem of calculus tomorrow. For now, it's important to see that definite integrals and indefinite integrals are different things. Remember, if I ask you to find the derivative, that was another function. But if I have asked you to evaluate the derivative at a given point, then that would give you a number. Similarly, a definite integral is a number. It's the area. If you have a non-negative function, then the definite integral is the area bounded by the vertical lines A and B, whereas an indefinite integral or an antiderivative is a whole family of functions. And that's why we had, on every derivative, antiderivative, we had the plus a constant, because that constant didn't change the derivative of the function. A sufficient condition for a function to be integrable on an interval from A to B is just that it's continuous from A to B. If you have a function that's continuous from A to B on the closed interval from A to B, then the function is integrable from A to B. So the very first problems in the homework just say, take these limit as the width of a rectangle goes to 0 of each Riemann sum. This is the Riemann sum right here. So take the limit of that Riemann sum as the width of a rectangle goes to 0 and write what definite integral that limit would be equivalent to on the closed interval from -1 to 5. Now this is going to be easy. It's the understanding what it means that is difficult, not the doing it. On number 12, if we just said our variable that's changing here is c sub I, c sub 1 would be, would be 0. C sub 2 would be something really close to 0. Doesn't have to be 1, but maybe 0.001, and then C sub 3, C sub 4, C sub 5, on and on. I forgot, I don't know what the rest of that sentence was. Anyway, number 12 said, write that limit of the Riemann sum as a definite integral from 0 to 3. That would be the integral from 0 to 3 of square root of, this is x squared plus 4. And then the delta x is the same as dx. In the section that we talked about differentials, we said dy over dx is the derivative of a function, and when you multiply both sides of that function by dx, then you have the differential dy equals y prime dx. This is the derivative that I'm going to anti-differentiate, and this is the dx, which is the differential in x. Number 14, that is hard to read. Is that 2 minus, what is that? Oh, that's 2 to the negative c sub I sine of c sub I on the interval from 0 to pi. So to write that as a definite integral, it would be the definite integral from 0 to pi of, the variable of integration is x, because my partition is given to me in terms of x. So this would be 2 to the negative x sine of x. And then dx, which is the differential in x. So that's all we have to do in the first problems. Write the limit of a Riemann sum as a definite integral. And then, let me see. I don't have that example 2 with me. Oh, that's why I said see page 309. I don't have page 309 with me. But if I had a function that was negative in some places and positive in some places, and I integrated that function from x equals a to x equals b, then that definite integral from a to b couldn't be area, because the definition of area includes the conditions that the function be non-negative on the interval from a to b. If the function is negative for part of that interval, then integrating from a to b doesn't give you the area. Actually, definite integrals can give you a positive number, can give you a negative number, or can give you 0. If you had the exact same amount of area below the x-axis as you had above the x-axis, then, and if you integrated from, let's say that was some function we were integrating from 2 to 7, then the value of that definite integral would actually turn out to be 0, because the amount of area below the x-axis is the same as the amount of area above the x-axis, and they cancel each other out. So that would be an example of an antiderivative whose value would be 0. For a definite integral to be interpreted as area, the function must be continuous and non-negative. So we already have that definition of area using the limit of Riemann sums, and now we're saying the limit of Riemann sums is the definite integral, and so this is the last leap. It's like saying if A equals B and B equals C, then A equals C. We're saying if the area is this Riemann sum, and that Riemann sum is this definite integral, then that definite integral is area. As long as you're integrating a function that's continuous and non-negative on that interval. So if I ask you to find this area, the area under this parabola is 4x minus x squared. If I ask you to find the area bounded by the function 4x minus x squared, the x-axis, and the vertical lines x equals 0. X equals 0 is just the y-axis. So bounded by the lines x equals 0 to x equals 4, you would just find the value of the definite integral from 0 to 4 of 4x minus x squared dx. So the next problems say write a definite integral that represents the area of the region. Don't evaluate the integral. We don't yet know how to evaluate this integral from 0 to 4 of 4x minus x squared. I don't know how to find that value. I'm going to know how to find that value tomorrow. But for today, we just want to set up an area as a definite integral. So on number 18, I have the half parabola, y equals x squared, and I want to find the area bounded by that piece of parabola, the vertical lines x equals 0 and x equals 2. What definite integral would find that area for me? What would be my upper and lower bounds of integration?
Zero and 2.
Yeah, my vertical line 0 to 2, I would integrate from 0 to 2 the function dx. The x squared gives me the height. If I broke that into a bunch of little rectangles, then f of x would give me the height of each rectangle, and dx would give me the width of each rectangle. And the definite integral from 0 to 2 of x squared dx would give me all that area. Number 22, I have the function tangent x, and I want the area bounded by tangent x from x equals 0 to x equals pi over 4. Miss Grace, can you give me the definite integral that would give me that area?
From 0 to pi over 4.
Mm-hmm.
Tangent x times dx.
Yep.
Or dx, yeah.
Yeah, exactly. And you read that the definite integral from 0 to pi over 4 of tangent x dx. We don't know how to evaluate that, but if we did, which we will tomorrow, then that would give me the area shaded in number 22. Now, I haven't actually been checking these conditions, and I should have. The two examples we just looked at were both continuous functions that were non-negative on the interval that we were given. So the only reason we can set up this area as this definite integral is because that function x squared is above the x-axis from 0 to 2, and it's continuous. Number 26. Mr. Joseph, I want an definite integral that will give me the area bounded by the curve 2e to the negative x from x equals 0 to x equals 2. What definite integral would give me that area?
From 0 to 2.
Mm-hmm.
Kind of hard to see that. 2e to the negative x
Yep.
times dx.
Yep, absolutely. So now I kind of understand this definition, and I understand that that's what the definite integral is. And so I understand that this definite integral would give me that area as long as my function is continuous from a to b and non-negative from a to b. If I have a function that is below the x-axis in some places in that interval and above the x-axis in that interval, I can still find the integral. I can still evaluate that from 2 to 7, whatever that function is, dx. But if I have drawn this so that these two areas are identical, then the negative value, let's say, am I getting too complicated? Yeah, I don't want to get that complicated. If I wanted to find this area, which is what we'll start out with in Calculus 2, I would actually have to find this point where this x-intercept, actually. Find the x-intercept, and then let's say that x-intercept turned out to be 4. Then I could integrate from 4 to 7. That would give me the value of this area, and I could integrate from 2 to 4, but if I did, I would get a negative answer. So I need to take the absolute value of the integral from 2 to 4 and then add it to the integral from 4 to 7 so that they don't cancel each other out. That would give me these two areas added together. All right, what's next? Ooh, this is cool. I said a minute ago that if I wanted the area of this shaded region bounded by this concave down parabola, the vertical lines x equals 0 and x equals 4, I can set up a definite integral for that. But I don't yet know how to evaluate that. The only way I could evaluate that is if this was some regular shape that I had a formula for in geometry. So what number 28 and number 32 give us is two shapes that we can evaluate this definite integral using a formula from geometry. For example, number 28, I want to find the value of the definite integral from -3 to 4 of the function 9 dx. This is my function. It's just a constant function, 9. So if I graph y equals 9 from -3 to 4, that would be a continuous function, and it would be non-negative on the interval from -3 to 4. Here's my vertical line, x equals -3. Here's my vertical line, x equals 4. And here's the area that that definite integral would represent. So how could I find the area of that rectangle? What's the length of that rectangle? Yeah, from -3 to 4 is 7 units. And what's the width of that rectangle? Or actually, here I'd probably call it height instead of width, but it doesn't matter. What's the height or the width of that rectangle?
9.
9. So what's the area of that rectangle?
63.
63. And since this function is continuous and non-negative from x equals -3 to x equals 4, that's what the value of that definite integral would give me. It would give me the area of that rectangle. The only way that I know how today, the only way I know how to evaluate that definite integral is by using a formula for area of a rectangle. If that had not given me a shape that I knew a geometric formula for the area, then I could not have evaluated that definite integral. Tomorrow we'll find out how to get that same answer, even if the function does not yield some shape that I have a formula for in geometry. All right, let's do one more of these. The integral from 0 to 3 of 8 minus 2x. Ooh, I accidentally left off my dx. The only way I can evaluate that definite integral is if when I graph y equals 8 minus 2x from x equals 0 to x equals 3, it gives me some shape that I know the formula for the area. So let's see. If I'm just going to make a little XY chart here and say if I let x be 0, what would y be? That one's too easy for you. If I let x be 3, then y would be 8 minus 6 is 2. So the endpoints of the interval would be 0, 8, and 3, 12. I think I'll count by 4s. On my y-axis, and then just count by 1s on my x-axis. 0, 8 would be the left endpoint, and 3, 2 would be the right endpoint. What's the shape of this graph from 0 to 3? Actually, what's the shape of this graph over its entire domain? Is it some kind of curve from this point to that point? Maybe a piece of parabola or something? Y'all, what kind of function is this?
Linear.
It's a linear equation, so it's a line between those 2 points. And Hold on just a second. I wish I hadn't counted by fours, but I want to find the area bounded by this shape. What is that shape?
Triangle.
Not really, and that's why I wish I hadn't counted by fours. You can see it better in this picture where I just counted by ones. You can tell it's a shape that's a lot taller here than it is here. I didn't mean to be showing you that. You remember the name of that kind of shape? That has a little base and a big base that are parallel to each other. That's a trapezoid. Yeah, that's a trapezoid. And the formula for area of a trapezoid it's like the area of a rectangle. It's the average, let me see how I want to say this. The average base height times the width if I call this little base my B1 and this big base my B2 and my width is from 0 to 3, the width of that trapezoid is just 3. How do I find the average height of base 1 and base 2? How do you find an average of any two numbers?
Add them together and divide by 2.
Yeah, so if I just add the height of base 1 to the height of base 2 and then divide it by 2, that'll be the average base height. And we've already said my width is 3. So what is the height of this base?
Two.
Yeah, that's the point 3, 2. So that height is 2. And what's the height of this larger base? 8. And 10 divided by 2 is 5. 5 times 3 is 15. 15 is the area of that trapezoid. And because that function is continuous and non-negative from 0 to 3, then that's what the value of this definite integral represents. This definite integral would be that area of 15 units. And again, the only reason that we were able to evaluate that definite integral is because when we graphed the function from 0 to 3, it turned out to be a shape that we had a geometric formula for. All right, there's only one other thing in this section. Properties of integrals. Let's see these real quickly. If f is defined at some vertical line or some point, x equals a, then if we integrate from a to a of the function, If I was just integrating from 0 to 0 of this function, what do you think the area beneath this line from x equals 0 to x equals 0 is?
Nothing.
Yeah, nothing. There's no area under a point. So if we integrate from a to a of a function, dx, we just get 0. There's no area under a point. If f is integrable on the closed interval from a to b, then the integral from b to a is going to be the opposite of the integral from a to b. And that's kind of what I was saying here. If I wanted this area, I couldn't just say integrate from 2 to 4, because if I integrate from 2 to 4, it's going to give me a negative value. But if I take the opposite of that negative value, or the absolute value of that negative value, then it would be the area bounded by the x-axis in that curve. I don't know why my voice has gotten so raspy. It's getting on my nerves. When I integrate from a to b, I get the opposite of what I would if I integrated from b to a. And this property just says you can integrate, or you can evaluate definite integrals from term by term. Just like we could differentiate term by term, we can integrate term by term. If c is some point between a and b, and we want to evaluate the integral from a to b, if we know the value of the integral from a to c, and we know the value of the integral from c to b, then we can just add those values together and get the integral, or the definite integral on the whole interval from a to b. This property says if I have a definite integral of a constant times a function, I can just bring the constant out front, just like we did with derivatives. If I wanted the derivative of 3x squared, I can just keep up with the 3 and take the derivative of the x squared. And actually, this is the property that says definite integrals can be evaluated term by term. You can find the definite integral for the first term and then the definite integral for the second term. So the last problems give us two things. Number 42 gives us the integral from 0 to 3 of some function. I don't know what the function is, but the definite integral from 0 to 3 is 4. And the definite integral from 3 to, that's supposed to be 6. The definite integral from 3 to 6 is -1. So they're giving us these two definite integrals and asking us to find the integral from 0 to 6 of that same function. If I know the value from 0 to 3, and I know the value of the definite integral from 3 to 6, how would I find the value of the definite integral from 0 to 6? If c is some point in between a and b, and I want to integrate from a all the way to b, I can integrate from a to c, and then from c to b, and add those two values. So if I want to integrate all the way from 0 to 6, and I know the integral from 0 to 3, and I know the value of the integral from 3 to 6, then I could just add those two values to get the integral over the entire interval from 0 to 6. I can add the 4 and the -1, and the value of that definite integral would be 3. Now, the fact that the integral from 3 to 6 has a negative value tells me this function is below the x-axis from 3 to 6. It's above the x-axis from 0 to 3 because the value of the definite integral is positive, but it's below the x-axis from 3 to 6 because the value of the definite integral is negative. All right, the B part says find the definite integral from 6 to 3. Well, if we know the definite integral from 3 to 6 is -1, what's the value of the definite integral from 6 to 3? If the definite integral from B to A, or not if, but the definite integral from B to A is the opposite of the definite integral from A to B. So if the definite integral from 3 to 6 is -1, what's the value of the definite integral from 6 to 3?
+1.
Yeah. What's the definite integral from 3 to 3 of f of x dx?
0.
Yeah, there's no area under f of x from 3 to 3. And then part D, if I have the definite integral from 3 to 6 of some constant times the function, I can just keep up with the function, or excuse me, the constant, and multiply it by the value of the definite integral from 3 to 6. The definite integral from 3 to 6 was -1. So the area, or the value of the definite integral we're looking for is 5 times -1. All right, last one. Number 44 says the definite integral from -1 to 1 of some function f of x dx is 0, and the integral from 0 to 1 of that same function is 5. How would we find the definite integral from -1 to 0? How could we use these two values to find that? This one is from -1 to 1, and that one is from 0 to 1. So how would I just find -1 to 0? I just want from here to here. I know this whole distance is 5, and no, I'm sorry. From here to here is 0, and from here to here is 5. What does that mean this has to be?
-5.
Yeah. It's this whole thing from here to here is 0, and this little part is 5. Then this little part would have to be -5 for the whole thing to be 0. The B part, find the definite integral from 0 to 1 of f of x dx. What is this term? What's the value of this term?
5.
That's 5. And then what's the value of this second term from -1 to 0?
-5.
Yeah, that's what we got in the A part. So 5 minus -5 is 10. this integral from -1 to 1 of 3 f of x dx? Well, without the 3, what's the value of that definite integral from -1 to 1?
0.
That's one of the things we were given. So this is 3 times 0, or just 0. And last one, the integral from 0 to 1 of 3 f of x dx. Where would we get that?
The other value, which is 5.
Yeah, from 0 to 1 of just the function, the definite integral is 5. So this definite integral in the d part is 3 times 5, or 15. All right. Did y'all all look at the email that I sent last night about practice test and the test?
Yes.
Okay, if you haven't seen that email, look at it, because I did this weekend, actually yesterday, I made test 4 in my math lab, and I made practice test 4 to give you, I mean, do the problems that I gave you on the written practice test also. That's just extra practice, but the practice test in my math lab has 25 problems. The real test in my math lab has 12 problems. If you can do the 25, then you can do the 12. So tomorrow we have our last section to discuss, 5.4. And then Wednesday, I will answer any questions you have from the practice test, either the printed one from Momentum or the one in my math lab. And then your test is, you are not going to need 8 to 10 to do 12 problems, so I just made it 8 to 9:30. Honestly, it'll probably take you about 45 minutes. Maybe some of you will do it in 30. All right, so be working on that so you can ask me some good questions Wednesday. And your homework for tonight is that. All right, I appreciate y'all hanging with me. It's been a rough, not as fun way to end the semester as if we had all been together in the classroom, but that's just what it is, and we rolled with it, and I appreciate you. I appreciate your hard work. Y'all have a good day, and I'll see you in the morning, okay?
Bye.
All right, see ya.
Bye-bye.
Bye.